Well, let me first say how delighted I am to be back in London. My own children were born here longer ago than I like to think about, and for me, the experience of childhood is very connected with the experience of being in London. Let me start out by saying something about the idea of a philosophical baby. Why would you put those two things, philosophy and babies, together? And in fact, if you looked at most of the history of philosophical thinking, those two things were not perceived as going together very much. So let me just put this on. I'm just going to put my clock up. Okay. So for most of the time, those two things were not perceived as going together very well. In fact, you could read 2,000 years of philosophy and think that human beings reproduced by asexual cloning. I looked in 1967 Encyclopedia of Philosophy, and there's no mentions at all of children or parents or mothers or fathers. Lots about the morning star and the evening star, and lots about angels, but not very much about children. And that's true in spite of the fact that for most people, children and their relationship to children are among the deepest and most profound experiences that we'll ever have. In the past 30 years, and when philosophers and psychologists and psychiatrists did talk about children, they talked about children as being sort of terribly defective adults. So even the great developmental psychologist Jean Piaget described young children as being irrational, pre-causal, egocentric, amoral, solipsistic. You get the idea, right? In the past 30 years or so, a new science has completely overturned those ideas. And every year we've discovered that children both know more and learn more than we ever would have thought possible in the past. In fact, an interesting sort of anticipation of this new view of the babies is very relevant to me. This is actually Dove Cottage in Grasmere, what I was visiting for the last week. And there was a kind of anticipation. The first real vision, I think, of what children's minds could be like actually took place in England by William and Dorothy Wordsworth, who both recognized the splendor in the grass and the glory and the flower and the trailing clouds that were really characteristic of children's minds and imagination. And this tiny, crowded cottage you could think of as being sort of the first children's museum, at least in England, maybe not in London. It was full of 2, 3, and 4-year-olds running around and providing poetic inspiration to William Wordsworth. Now, from a scientific perspective, one of the questions that we can ask about children, one of those questions that those philosophers could have been asking but didn't, is why do we have children at all? Not the obvious answer, which presumably everybody here knows about, but why is it from an evolutionary perspective that we have this period of childhood in which children are so dependent and so helpless and fundamentally so useless? Babies don't bring in any money, they don't help the family economy, and of course when preschoolers actually try to help, they make things even worse than they were before they started. They're especially useless. And this is a particularly important, I mean, not only are they useless, but we have to put so much time and energy into just keeping them alive. You might say they're worse than useless. Now, why would this be? Why would we see this period of childhood? And of course, it's particularly striking for human beings because we actually have a longer period of immaturity, a longer childhood, substantially longer than that of any other species. My son is 25, and at least until they're 25, we're taking care of them and writing their tuition checks and generally looking after them. Well, it turns out that the evolutionary answer to this comes from work that started out not being about human beings at all, but being about birds. And what people who evolutionary biologists who studied birds discovered was that there's this striking correlation between the period of childhood, how long a period of immature helplessness an animal has, how large their brains are, and how clever the adult animal is. And the sort of poster animals for this are these birds. This is actually a New Caledonian crow. This is a crow that lives on an island off of New Zealand. And New Caledonian crows in particular, but crows and corvids and jackdaws and ravens in general, are incredibly smart birds. This is actually a bird on the cover of Science magazine who's learned how to bend wires to turn them into tools to get food. In fact, the New Caledonian crows are as smart as primates, as smart as chimpanzees in the most recent studies. Here, on the other hand, is our friend the domestic chicken, and with apologies to any chicken lovers in the audience, chickens and ducks and geese and turkeys and all of their relatives are basically as dumb as stumps. So they're very good at pecking for grain. They're not much good at doing anything else. And the chicken babies are mature within weeks or months, whereas the crow babies take as long as a year to fledge. And the New Caledonian crow babies actually take as long as 2 years to fledge, which is a very long time in the life of a bird. This isn't just true for crows and chickens, it's true for mammals in general. It's even true for marsupials like quokkas and kangaroos. Well, the most recent studies of the New Caledonian crows might suggest an answer to this question about why you'd see this correlation between the cleverness of the adults and the immaturity of the young. Because it turns out that in the wild, what these New Caledonian crows do is fashion beautiful tools out of palm leaves. They take the palm leaves, they strip them off, they taper them so that they come to a thin end and have a thick end, and then they take the tools and they put them in holes and use them to get insects. Now, the interesting thing is, if you actually watch those young crows in that first 2 years, they try to do the same thing, and they're about as helpful as your 3-year-old is when he decides that he's going to sweep up the kitchen. They drop them on the ground, they strip them from the wrong side, they hold them by the wrong end. They're really completely useless at using these tools for 2 years. And the mom crows, in fact the mom and dad crows for crows, sort of sit there and tap their feet and wait for the crows to straighten out enough, and in the meantime cheerfully do the equivalent of tuition checks for a crow, which is drop insects into their mouths for that 2 years. And what that suggests is that what's happening in that period is that the children are actually mastering the skills that they're going to be able to need as adult crows. And the thought is that there are these different evolutionary strategies that different animals can use. Some, like the chickens, are beautifully adapted to one particular evolutionary niche. Others, like the crows, aren't terribly well adapted to any one niche, but are very good at learning about the environments, the new and varied environments in which they find themselves. And that's a terrific strategy, but it has one big drawback, and the big drawback is until you do all that learning, you're going to be helpless. So you don't want to have the mastodon charging at you and be saying to yourself, a mastodon, I wonder if maybe a slingshot would work, or a spear. You actually want to have done all of that learning before you're actually facing the realities of adult life. So there seems to be this kind of evolutionary division of labor where children are like the research and development division, as I heard before, are like the research and development division of the human species, and we're production and marketing. So they're the blue sky guys who just get to learn, to find out about things, and we take those things that we learned when we were children and actually put them to use. So children are for learning from this perspective. That's what they're designed for. That's what they're all about. And of course, if you think about we human beings, we're way out on the end of the spectrum on all of these dimensions. We have by far the largest brain, and we depend more on learning than any other species. It appears that we evolved because our environment became extremely variable. We're good at dealing with a wider variety of environments than any other species. And our children are immature and dependent for longer, substantially longer than those of any other species. And we put more time and energy and care in just keeping them alive. Well, if this evolutionary picture is right, if we can think about childhood as being an evolutionary period designed for learning as opposed to the adults who are designed for planning and acting, we might expect to actually see this in children and adult brains. And in fact, we do. So here's a famous slide of human brain development. And this slide is showing the number of synapses that are being created at various ages of development. Synapses are the connections between neurons in the brain. And what you can see is that across the brain, there's this early period when many, many, many new connections are being formed. And then there's a point at which the connections that have been formed become stronger and more efficient and more effective. And connections that could be formed but haven't just disappear. They're pruned. They no longer exist. So what you see is, even from a neurological point of view, you see an early brain which is designed to be plastic, flexible, good at learning, and then an older brain which is very good at doing the things that it does effectively and efficiently and swiftly and well, but is not very good at going out and learning something new or being flexible or trying something else. So we see this even in the context of brain development. So what I'm going to argue today is that this early brain and this early developmental period is really designed for learning. And what I'm going to suggest is that when we actually look at what children are doing, we can also see them as creatures who are really designed for learning. And the thing that they do the most is the thing that we call play. And of course, we all just take it for granted that children play. It seems like a kind of obvious thing for children to do. And of course, for a long time, intuitively, people have felt that there was a connection between children's play and their cognitive capacities. But rather surprisingly, we haven't actually had really good, clear scientific evidence for this until relatively recently. So today I'm going to focus on two ideas. One of them is a link between children's exploratory play and their ability to learn about the causal structure of the world, to do what's a kind of precursor of scientific learning. And I'm also going to talk about their pretend play and its relationship to a particularly powerful kind of reasoning and thinking and learning, counterfactual thinking. All right, let me start out by introducing you to the Blakey detector. This is our incredibly expensive piece of laboratory equipment. It probably costs something like $29.99. One of the big questions you could ask is, why is it that for all those years people got children and babies so wrong? Why was it that people were so wrong about what babies and children could do? And I think the answer is that they didn't ask children what they knew in children's own language. So if you ask a 12-month-old what they know about the world, they're not going to tell you anything that sounds very intelligent. And even if you ask a 3-year-old, you're likely to get a beautiful monologue about ponies and birthdays and sort of lovely stream of consciousness poetry, but you won't get anything that sounds like it's very rational. What we had to do was figure out how to get children to tell us what they know by looking at what they did rather than looking at what they said, and to ask them what they know by giving them real-life problems rather than simply asking them, say, something in a questionnaire or as an abstract hypothetical question. And the way we do that to try and figure out how children are figuring out the causal structure of the world is to use this little machine. So with this little machine, what we can do is present children with patterns of statistical data, the kinds of patterns of statistics that you'd use as a scientist, for example, and then see what kinds of conclusions children draw about how the machine works based on that pattern of data. And let me show you just one experiment out of now dozens, even hundreds of experiments that have been done looking at this. In this experiment, what we did was to try and see if children could understand the fundamental ideas of statistics. So what we did was first we asked the children, how do you think this machine works? And the children, just like probably everybody in this audience, thought that what you should do is put a block on the machine and make it work. But then we showed them these two patterns of data. So first the children saw that the block A, the red block, actually made the machine go 2 out of 3 times, but it did it without actually making contact with the machine. So that provides data that actually contradicts the children's initial hypothesis. And then we showed the children this other block, the blue block, actually makes the machine go 2 out of 6 times, but it does fit the children's initial hypothesis. So now there's a kind of contradiction between what the children initially thought and the probabilistic data they're getting. If the children were being like good scientists, they say, well, the statistics actually suggest that this block has a stronger causal power. There's a stronger causal connection between this block and the machine than the other block in the machine. Now, we can't ask the children, have you calculated whether the conditional probabilities are consistent with a hypothesis of causal strength at above 0.05 probability? But what we can do is we can ask them to make the machine go. And when we do that, what we see is that the children are actually choosing to wave the block on top of the machine more often than they are to actually put it on the machine. And they actually do so exactly in proportion to the probability of one option making the machine go or the other option making the machine go. And in an experiment that we've just published, we've shown that we can actually change that probability in a very fine-grained way, all the way from sort of 50% up to 90%. And the children's responses will track that probability in a beautiful, detailed way. We've also shown in our latest experiment, this experiment was done with 4-year-olds. We've shown the same effect with 24-month-olds. So remember, 24-month-olds, these are just barely 2, and even 4-year-olds are just barely adding and subtracting, but unconsciously they seem to be doing the math to calculate these statistics and using that to actually make things happen in the world. Well, that is, as I say, just one token of a whole range of experiments that show how amazingly sophisticated children are at doing this kind of probabilistic inference. But of course, in that case, we're actually giving them the data. Could children actually discover the data for themselves? So what people have done is to actually give the children the machine and the blocks and just see what do they do. And here's an example from an experiment like this by Christine Laguerre at the University of Texas at Austin.
This on the box and this on the box.
And what she did was she just showed the children the machine, and she asked them to explain how the machine worked.
That light up the box.
Mm-hmm.
How about this? How about the other side? Oh. Nothing. This one's lighting up, and this one's not. So that means what's making this light up? I don't know.
Now this is where I think the true resemblance to scientists comes up.
Oh, it's because this needs to be like this, and this needs to be like that. That's why. Oh, probably the boxes are the wrong way.
Okay, this is his suggestion.
What should we do now?
Oh, because the light goes only to here, not here. Oh, the bottom of this box has electricity in here, but this doesn't have electricity. It's lighting up. So we need to put 4. So we need to put 4 on this one to make it light up and 2 on this one to make it light up.
Okay, so that's an incredibly adorable, articulate little 4-year-old. But it turns out that he was actually quite typical of the 4-year-olds that Christine studied. So when you took the 4-year-olds, gave them an anomaly, and just asked them spontaneously to explain it and let them loose, what they did was to generate all these hypotheses about how the system could work. And you'll notice that in the 2 minutes of that little video, the little boy goes through 8 different hypotheses, many of which are actually kind of unlikely ones, not ones that I think any adult would get to. And in fact, in some experiments we've just published, it turns out that children, when you give children an unusual system, a system that works in an unexpected way, you give that to 4-year-olds and to Berkeley undergraduate students, the 4-year-olds are actually much more likely to figure out that the machine works in an unexpected or unusual way than our otherwise very clever undergraduate students are. So these kinds of experiments suggest that when children are just doing the kind of everyday play, getting into everything, what they're really doing is doing a bunch of experiments. But there's also been some more systematic kinds of experiments like this. This is one by my ex-graduate student Laura Schultz, who's now at MIT. This was actually done at the Boston Children's Museum. And what she did was take the Blakey detector, and now what happens is in the first part of the experiment, the children either see, so take the Blakey detector, and she has little pop beads. You've probably all seen pop beads, those little beads that stick together. And in the first part of the experiment, the children see either that all of the beads make the machine go, or they see that some individual beads make it go and some don't. Now, that second question actually raises an interesting problem for the children. Why is it, and which beads make it go and which ones don't? Then what she did was simply give the children 2 beads stuck together and let them play with the machine. And what she discovered was that in the some beads, but not the all beads case, the children would actually pull the beads apart and test them separately. And then they made the problem even harder by actually gluing the beads together. And now what the children did spontaneously was to do this. They'd take one end of the beads and put it on the machine, and then take the other end and try it on the machine. But in both cases, they only did that in the some beads condition, where it would really tell them something about how the machine worked. So again, just in their spontaneous play, no one's telling them anything, no one's asking them questions. They're doing just the experiments that will tell them the most about the questions that they really need to answer. Now, one question you might ask is, how does this kind of spontaneous exploratory play, how does that connect to the kind of teaching that we typically think of doing when we have children in schools? And here's another experiment from Laura's lab that tested this. In this experiment, what happened was that she showed the children this new toy that had 4 interesting things that it could do. It could squeak, it could light up, it could play music. And she introduced the toy to the children in 2 different ways.
Hey, Scarlett. My name is Sammy. Hi. The museum gave me this really weird toy. It's so weird. I've never seen this before. Oops. Did you hear that? Did you see that? Weird. I've never seen that before. That is so weird. This is a really cool toy, Scarlett. I want you to play with it and see if you can figure out how it works, okay? Can you let me know when you're done playing?
Okay, so the experimenter says it's this cool toy, no one knows how it works. By accident, it squeaks. And then she just leaves the toy with the children. And what happens is that Scarlett, in the course of the next 2 minutes, explores the toy and finds out all the things the toy can do. She figures out how the squeaker works, she figures out how the light works, she figures out how the mirror works. And that's quite typical of what children do when you let them play with the toy. Now, here's the other condition. Now, this is almost the same.
This is my toy. Isn't it cool?
But now the experimenter is being a good teacher. She's actually going to show the child how the toy works.
Isaac, watch this. Did you hear that? Can you let me know when you're done? Okay, great.
So the child tries the squeaker, and then he tries the squeaker, and then he tries the squeaker, and then he tries the squeaker. And believe me, as long as this video goes, all you're going to see is him squeaking the damn squeaker. This also also turned out to be typical of what the children did. So when the toy was introduced to the children in a pedagogical way by saying, this is what my toy does, and I'm going to show you what the toy does, the children quite rationally concluded that what the toy did was the thing that had been demonstrated to them, and never actually went and explored and discovered all the other potential things that the toy could do. And several other experiments in my lab have shown in the same way that pedagogy is really a kind of double-edged sword. When we tell children things, it gets them to the solution more quickly, but the very fact that it's gotten to the solution more quickly keeps them from exploring in the way that they might have done otherwise. Let me give you an example of an even more complicated kind of causal system and children learning about it through exploring. This time what we had was a little box that had a switch on the side and then 2 gears on the top that went back and forth. And what happens is you flick the switch and the gears go together, and then you flick the switch back and the gears stop. Okay. Now, even this very simple system could actually work in lots of different ways. Here's all the causal possibilities. So it could work by having the switch make the yellow one go, which makes the blue one go, or vice versa, or it could be that the switch makes both of them go. And if you do certain kinds of experiments, you can actually decide which one of those complicated causal possibilities is right. So for example, suppose you do this. Suppose you take the blue gear off, and now you flick the switch, and the yellow gear goes. And now you take the yellow gear off, and you flick the switch, and the blue gear doesn't go. Now you actually know something. In fact, now you know exactly how the machine works, because what you know is that only this possibility is actually the correct possibility. Now, I can see people looking anxious, which is what typically happens when we show grown-ups this slide. Don't be anxious about it. The undergraduates, the brilliant undergrads, the brilliant 25-year-olds at Berkeley have just as hard a time with this. But the 4-year-olds don't. So the 4-year-olds actually solve this problem when we give them this data. Okay, so one of the things, so far I've been showing you the way that just everyday play, the sort of thing you see every 2-, 3-, and 4-year-old do, is actually giving children just the data they need to solve the problems they need to solve, in just the way that the very best scientists would be experimenting. But of course, the thing that's most important for children and babies to understand, in fact, arguably the most important thing for any human beings to understand, is not what's going on inside of a Blakey machine, it's what's going on inside of the minds of the other people around you. Again, great classic philosophical question, the other minds question is, how do you ever figure out what somebody else is thinking? And if you look around this room, really what you're seeing in this room are a bunch of bags of skin that are stuffed into pieces of clothing with little dots on the top that move back and forth and holes at the bottom that open and close and have breath coming out. But of course that's insane, right? That's mad. What we really see we see people with thoughts and perceptions and ideas just like ours. How is it that children can ever understand and come to understand what's going on with other people's minds? Well, again, the conventional wisdom was that even very young children were egocentric and had trouble taking the perspective of another person. But we thought maybe that was because we weren't asking children the question the right way. So a while ago, my student Betty Repicoli and I actually tried to see how could we actually ask children questions like whether they understood what someone else wanted. It's a hard thing even for adults to understand. And the way we did it was that we gave them 2 bowls of food, one bowl of raw broccoli and another bowl of Pepperidge Farm goldfish crackers, which are what in England you would call cheesy biscuits, delicious little salty crackers. And then what happened was that the experimenter made a face as she tasted each bowl of food. So half the time, for half the children, she'd act as if she really loved the broccoli. So she'd go, broccoli, I tasted the broccoli, and hated the crackers. She'd go, oh, yeah, crackers. And half the time, she'd reverse it. She'd act as if she liked the same thing that the children liked. And in fact, all the children, even in Berkeley, liked the crackers much more than they liked the broccoli. Then what the experimenter would do was put her hand out and say, can you give me some? Now here was the question, what would the children give her? Would they give her what she liked, the broccoli, or would they give her what they liked, the crackers? And what we discovered, we did this with 15 and 18-month-old babies, and what we discovered was that the 18-month-olds would give her the crackers if she liked the crackers, and the broccoli if she liked the broccoli. So these 18-month-old babies had already learned something very deep about the human condition, which is that sometimes we want different things. And even more amazingly, that when people want something different than you, you should still do what you can to get them to get what they want. On the other hand, the 15-month-olds looked at her much longer when she liked the broccoli, like they couldn't really believe that this could be true. But nevertheless, they always gave her the crackers. So not only had these 18-month-olds understood this profound thing about other people's minds, but they somehow seemed to have learned it between the age of 15 months and the age of 18 months. And in fact, in some experiments that we're doing in my lab right now, we've actually shown that by giving 15-month-olds information, data about lots of people, different people liking different things, we can actually accelerate their understanding of this basic fact about human nature. But another way, this whole area, what's sometimes called theory of mind, has been a big area of investigation in cognitive development and now in cognitive neuroscience over the past 20 or 30 years. And it turns out that all through life, but especially between about 18 months and about 5, children are discovering new things about how other people's minds work. Now, one way we think they're discovering them is by actually doing experiments, but there's another kind of thinking that seems to be even more important. And that involves doing not real experiments, but thought experiments. And Gareth mentioned Einstein. Maybe the most famous example of this is the fact that Einstein comes to his conclusions by doing things like saying, what would happen if a train were going at the speed of light? Things that couldn't possibly actually be true, but where you can calculate what would happen if that were the case. That kind of thinking, what philosophers call counterfactual thinking, seems to be one of the central things that gives us our human cognitive advantages. Because although it might seem sort of irrational to be thinking about things that aren't actually true, really, if you think about what we've done as human beings, everything around us depends on our thinking about things that aren't true. So everything in this room, the woven cloth and the carpentered edges, not to mention the lights in the computers, was imaginary from the perspective of a hunter-gatherer in the Pleistocene. None of these things existed. Everything in this room started out as an idea in somebody's head that wasn't true, that didn't exist. What we mean by imagination, which we often think of as being at odds with technology and science, is actually the most central thing you possibly could have in technology and science. The great technologist at Xerox PARC, Alan Kay, once said, the best way to predict the future is to invent it. And that's really that capacity to invent, to imagine possible futures and make them real, is one of the things that's the most distinctive kind of human capacity. Now, when we look at young children, one of the things that we see is that they're engaged a lot of the time in thinking about things that aren't true as well. When they do it, we call it pretend play. And between the ages of 18 months and 5, walk into any nursery and you'll see these princesses and ninjas and children off in these kind of crazy imaginary worlds. We just take it for granted that that's happening. But it's actually quite mysterious. Why are children spending so much time pretending? Now, the conventional wisdom was that they're spending so much time pretending because they are confused about the relationship between pretense and reality. But it turns out that that's not true at all. If you ask children, they understand the difference between the real world and fantasy worlds perfectly well. It's just that if they have a choice, they would rather live in the fantasy world than in the real world. This is something you could hardly blame them for. This slide is actually an iPhone shot of some children in the Child Study Center, which is the nursery at the university where we do all of our research. And over the past year, they've started a new pretend game, which they call research. So what these children are actually doing is they have little clipboards that they've got, and they've got little name tags, and they go around the nursery and they go to the other children and say, I'm doing research. Do you want to come and play games with me for my research? So the children completely, I sort of love this. This has just happened when we started doing our studies of pretend play. So the children are actually pretending as a way of exploring the researchers, exploring the way that the children are pretending. So it's very, very meta. But this kind of pretend play is completely ubiquitous in children. One of the most dramatic examples of early pretend play is actually the phenomenon of imaginary companions or imaginary friends. And again, in sort of popular culture, imaginary friends are fascinating. They tend to show up in sort of one of two varieties. Either the really creepy imaginary friends, that's from The Shining, where the creepy imaginary friends, or they're sort of humorous imaginary friends, like Harvey, who was the imaginary friend, the 6-foot rabbit, who's the imaginary friend of Jimmy Stewart. In fact, in my own family, we have two stories that are of the scary and funny varieties about imaginary friends, and that I think are somewhat illuminating about why children have imaginary friends. So when I was growing up, I had an imaginary friend called Dunzer. And Dunzer was not actually an imaginary friend. He was more like an imaginary enemy. He was this kind of evil little dwarf who lived at the end of my crib. And who, in my mother's description, just got meaner and meaner and meaner as time went on until I refused to go into my crib at all. My mom, finally at her wit's end, said, well, how about if you go into Adam's crib, Adam being my 1 year younger brother? And I said, that's fine. Dunzer never goes in Adam's crib. So they went to put me in Adam's crib and then picked up Adam, who at that point was about 1.5 years, to go into my crib. And he immediately pointed to the same spot where Dunzer had been and started to cry and hold on to my mother and refused to go into the crib. So that's the scary Henry James Gopnik imaginary friend story. Now, that little boy, perhaps unsurprisingly, grew up to be a writer. And he actually writes for The New Yorker. And his daughter, when she was about 3, also had an imaginary friend. Her imaginary friend was called Charlie Ravioli, wonderful imaginary friend names. And the distinctive thing about Charlie Ravioli was that he was too busy to play with her. So growing up in literary Manhattan, she would say things like, I bumped into Charlie at the coffee shop today, but he had to run. And she would leave messages on an imaginary answering machine. So she'd say, Charlie, it's Olivia calling. Could you get back to me? And then she would turn to her father and sadly say, I always get his machine. Now, this is a funny story. But it's actually also an illuminating story because our reaction to that story is that it tells us something, and it told Olivia, the little girl, something about how the people around her actually function. So it's an important thing to know, as it's like from the laughter, I can see lots of people here have been to New York. When you go to New York, it's important to know that your best friends are not going to be able to meet you until sometime in the middle of next year, right? And it turns out that that kind of idea, the idea that Olivia was doing a kind of thought experiment about what it would be like to have a friend in New York, working out the consequences of that experiment, that actually turns out to seem to be true. So Marjorie Taylor, who's a wonderful psychologist at the University of Oregon, did these lovely experiments in which she went out and just asked children about their imaginary companions. And she discovered that somewhere between 60 and 70% of just typically developing 4-year-olds had some kind of imaginary friend or other. And interestingly, it wasn't that the children were confused about whether the imaginary friend was real. As part of her technique, Marjorie actually went out and would come several times to make sure the imaginary friend was really consistent and asked the children, now, Gawk and the dinosaur's tail, is it purple or is it green? And after a while, the children would turn to her and say, you know, he's just pretend. He's not actually real, because they were dealing with this adult who was coming in and asking them questions as if they thought. And, you know, adults often get confused about the difference between fantasy and reality. And in fact, although my mom certainly told these stories as if her children were either clever or more crazy than any other children, in fact, it turns out that children with imaginary companions aren't any cleverer or more crazy than any other children. But they do have one interesting difference. they're better at those theory of mind tasks that I just told you about. They seem to have a deeper things like the broccoli and goldfish task. They seem to have a deeper understanding of what's going on in other people than the children who don't have imaginary friends. And pretend play seems to have this effect in general. And the idea is that these children, kind of like little Einsteins, are sitting and doing these kind of thought experiments about how other people work, how other people's minds work, what it would be like if you had an imaginary friend or an imaginary teacher or an imaginary enemy, and are working out the consequences of those things. And doing that kind of thought experiment, that kind of counterfactual thinking, actually seems to help children to understand what's going on around them. So just in the course of their imaginary play, in the course of their pretend play, children are solving these problems. And what we've been starting to do in my laboratory is to actually do a whole bunch of experiments trying to show that children actually can perform this kind of counterfactual thinking, this deep thinking about possibilities, when they're pretending in a way that they might not be able to do if they were actually out in a real serious life. So for example, and I'm actually going to subject you to a graph here because this is data that's hot off the presses back in Berkeley. So for example, one thing that we did was we actually took that gear toy that I described to you before, and what we did was we actually taught children how the toy worked. We taught them one of the causal structures we described before. You flick the switch, it makes the blue gear go, that makes the yellow gear go. And then what we did was we asked them about another possibility. So we said, how about if the toy didn't work this way? How about if the toy worked differently? How about if the toy worked worked this way? The switch made both of the gears turn. And now, how about if I took one of the gears off? What would happen to the other gear? So we asked them the question that way as a kind of hypothetical question, but we also asked the children the question as a pretend question. So we said, let's pretend that this machine works differently. Let's pretend that the way it works is that the switch switches and then both of the gears turn. Now, if I flick the switch and take off, now I'm going to pretend that I'm flicking the switch, and I'm going to pretend that I'm taking one of the gears off. What will happen? What should we pretend is happening to the other gear? And what we discovered was that when we asked the children the hypothetical question, they actually had quite a lot of trouble answering it. But when we asked the children to pretend, in their pretend play, they actually solved the problems. So they could figure things out. They could consider the alternative possibilities and crank through them and see what the consequences were when they were pretending, as it were, that the train was going at the speed of light, in a way that they couldn't if you asked them the question the way that you would ask a question in school, say, by just saying, all right, if this happens, then what will the consequences will be. And that's just one of several experiments that we've done recently, showing that children are able to think about possibilities when they're pretending in a way that they can't when they're just straightforwardly trying to make hypothetical inferences. Okay, so how does all this connect to the London Children's Museum? There's the statement for the London Children's Museum. What we've been discovering is that children, and especially young children, are actually designed to be explorers. They're designed to be learners. That's what they're all about. And the interesting thing is that the most dramatic evidence of those learning abilities comes not when you put the children in a school setting, but when you put them in a setting in which there are rich, complicated things for them to find out about and rich opportunities for them to find out about them. And that's exactly the setting that a children's museum, a place like the Exploratorium, which I've had a long association with in San Francisco, a place like the Boston Children's Museum, which is the museum that was giving people the squeaky toy. That's exactly the setting in which those kinds of abilities can be exercised. And there's increasingly few settings that are like that for children. even in nursery schools and preschools, there's increasing pressure to make those settings more and more academic, more and more pedagogical, more and more didactic. And there are fewer places where children can get a chance to exercise the sort of spirit of play, the spirit of inquiry, the spirit of exploration that our science is telling us is really crucial to their nature as children. Museums, children's museums, it's sort of surprising. I don't think anyone quite knew that this was going to happen. It's turned out that museums are places more than any other at the moment that have turned into the centers for that kind of exploration and play. And let me say finally, one of the advantages of this, I've been saying that the children are the brilliant R&D division. You could really think about the children, the difference between the children and adults as being like the difference between butterflies and caterpillars. They're different stages of the same being, except that they're actually the butterflies who get to flit around and explore, and we're the caterpillars that have to hump along our little narrow adult paths. But one really great consequence of all of this new understanding of children is I think it tells us that even as adults, we have the capacity to do this kind of exploration and inquiry and play. And one of the other great things about children's museums is not only that they're there for children, but that they're actually a space in which adults can be children, in which adults can explore and innovate and play in the company of those children. And that gets me back to my original slide of Dove Cottage. I think that was actually the great discovery that William Wordsworth made in the beginning of the 19th century. That sitting in that crowded room with all those children running about and making noise and falling into the fire and so forth, that it was in that setting that he could actually recapture that glorious sense of possibility that's really fundamentally central to our human nature. So let me end there, and thank you all very much for coming, and thanks to the museum or Museum to Be for inviting me.